Okay, for the DE students, I was explaining stuff to the on-campus students for lab tomorrow because I wasn't going to be here for their lab. Larry, in your class, asked if I would please try to do um, that one recording that was about this particular this particular set of slides. That was the one that accidentally I really messed up on. This one's very close to the same thing, so there's no reason for me to really redo it. If you really want to email me tonight and tomorrow, I'll try to find some time and a computer to do it. Okay. When we come back from fall break, which will be, let's see, what's today? It'll be Thursday next week, so we get a whole week off. I'm going to love having that Tuesday morning and not have to come in for an 8 o'clock class. Then let's talk about the midterm exam. And I'm hoping during the break I can set it up to be an online exam. I don't know if I'll be able to or not. I was just reminded that Project 1 says it's due October 5th at 11:55 p.m. Now, it is not a real difficult project, okay? But it does take a little while to do it. And I think you guys are going to at least need a few more days on that. This is an example of what I want, and these are the 3 expressions I want you to do this for. Everything in a one-word document. I'm going to have to change that date, which is going to push this date, and it's going to push this date, and it's going to push this date, and this one. This is the very last day of class. This is a big project, so I can't push it any further. This one is not too bad, but we do want to have some time to do that. So what I'm thinking is I'm going to push this one back. It'll probably be due around the 12th, and then this one will go the next to the 19th, and then this one will go to the 26th. So we'll just have to go boom, boom, boom to get these done. But these are not that difficult. The first 3 projects are not that difficult, and at any time you can ask me, and I can show you how to do some of that stuff in while we're in class. Now look, this is the second one. It looks like the same thing, but what I've done here is the first one I think was one of them is writing the VHDL for those, and the other is writing the using the schematic. And I don't remember which one it is yet or now. This one says using VHDL, so I would bet this one's the logic with the schematic. Yeah, so you put this in. And remember, if you're trying to verify this, it's going to be hard to verify it with Xilinx because it renames everything.
Right. So the first image that we have to create in our schematics, right? We have to create a schematic and then put any gates and all gates and all that.
Yeah.
Okay, the VHDL will create it.
Yeah, and you got to do that for these 3 expressions. So you got 3 expressions in that one.
Okay, so schematic.
And do not even bother to simplify anything. Let Xilinx simplify if it wants to. Okay.
So could we use the first Xilinx thing that we did and just put that in there, like we did because whenever we inputted that the one expression from lab 1 or 2, whichever one, if we input it in there, so that would make it for us. That's what you want us to do.
If you put in the VHDL, then if you looked in some of the RTL schematic, I think it shows some of that. This one is, no, this is one where I want you to put in the schematic. Okay, because in the next week, you come in, this is project one, you're putting in the schematic. The next week, you're taking those same expressions and you're doing it in VHDL. And now it will make those circuits for you, but it'll simplify them a great deal. Okay, and it'll change. See how I did DC A and B? I changed.
Why did it change it like that? It did that on the
I don't know why it does that. It does what it wants to do. There is one of them that's going to give you some weird warnings. I'm just going to tell you now. I used to do it just as a way. You guys are all good, and so are my DE class. But I used to do it as a way to find out where was my class. Where were they working? I mean, how far along had they gotten? Were they waiting till the last moment to do everything? Because one of them, the circuit simplifies to A. So Xilinx is asking you in errors and warnings, why are you giving me something that is actually I'm sorry, the DE students aren't seeing it, but it's A input, an input buffer, an I buff, a line that's connected to an O buff that's connected to F at the output. It says, why are you making me do this? Okay, so in so many words, when you read, when you know that, and then you read the errors and warnings, you understand why it's saying that. So I go ahead and get started on this. During break, I would like you to take a break. And again, if you have any more of these that I need to fix, just tell me these are the ones you need to fix. I am at the point where I believe you. Unless it's absolutely blaring and I go, whoa, wait a minute, those aren't the same. But if you tell me they are the same, I'm going to say, okay, they're the same. And I'm going to give you the credit for it. Most of you wouldn't lie to me anyway, and the ones that would, it's going to be your own problem, not mine. Okay, let's look at this one. This is about flip-flops and counters, and I know I don't have time to do it right today. Wait a minute, let me see how many it is. 79 pages. I probably don't have time to do it right, but I want to get through as much of it as I can. The ones that are the most important are D, T, and JK, because we don't use the others very much. But we're also going to look at the SR latch and the SR flip-flop, and look at some different asynchronous and synchronous circuits, and some with enables and loads. And it's that part with the enables and loads and the asynchronous and synchronous that I may wait till later to talk about. The difference between a latch and, I don't know if it says it in here or not, it says all kinds of stuff. I don't know what, but between a latch and a flip-flop, a latch doesn't have a clock or gate controlling when the output changes. The output changes when the input changes. So anyway, let's get started. The first one that's out there is the SR. These are the two different SRs that you can get. One's an active high input and the other's an active low input. Those are really the only difference between them. There are some SR flip-flops that are out there, or latches that are out there. Notice there's no gate or clock controlling these, so these we would call latches. There are none that are really used in industry, because it's really just something that was used for academia. So here's how we go through it. Now, I just came up with a way to get started on how they work, but if, and look where I started at the bottom of the list, if the current state is 0 and 1, so the output Q and the other one is not Q, okay, and that's by definition it's a 1. Now, can they both be 0 or both be 1? Sure. Sure they can. I mean, it's not going to blow anything up. Uh, but by definition, that's not correct. So by definition, we will call that an illegal state or something like that. But it's, for right now, if the current state is 0 and 1, and you are going to see so many different kinds of, uh, they'll call them truth tables or excitation tables, uh, for all the different latches and flip-flops that there are. You find one you like and understand and stick with it. Make sure it's right. Okay, so here it says if Q and Q naught are 0 and 1, and our inputs are 1 and 0, 1 on set and 0 on reset, and notice that 1 is on the set, that's down here, 0 is on the reset. What happens is the next state, it causes the output not Q to go low. Okay, well this is an OR gate. When we put a 0 here, we have to have at least one 1 to make this, wait a minute, I'm going to start getting myself all confused on these. I do it every time. For a NOR gate, if any input is 0, the output should go to 0, right? If any input is 1, let's see, that would, let's see, 1 and 1, then that would be a 1 here, but a 0 there. But if it's 0 and, okay, this one, because we had this before, there's this 1 on not Q. That 1 here and the 0 here, the 0 actually makes this one go, I'm messing it up again. That 0, it forces this output, I'm sorry, it forces this 1. Damn, which one is it? I'm getting myself all messed up. This 1 here is causing this to go to 0. Right? Okay, thank you. Because if these are both 0, then with the OR gate, the output would be 0. And before, the state before, it was 1. So if these are both 0, then the output for an OR would be 0, but for a NOR it would be 1. So then when I apply a 1, that causes this to go low. With that going low, this is low. Now we got 2 lows on the input here, and that will cause the output here to go high. So, okay, that made sense. So, or at least it did to me. I would not listen to that again. You'll just confuse yourself. Right? So here we got, what we should be saying here is that if we got 0, 1 at the inputs and we apply 1, 0, that's what we're going to get at the outputs. If we've got 1, 0 at the outputs and we change these around and put a 1 on the reset and a 0 on the set, it's going to cause it to to reset this latch. Okay, so it'll cause the one to go to 0 and the other one to go to 1, and we got the reset state. So this is a set state. It's always associated with the Q output. When Q is 1, it's set. When Q is 0, as it is now, it's in a reset state. Okay, then we get this one. This is our current, state. I just moved that from here to here, and I put 0, 0 here. And when I put 0, 0 on those inputs, it causes both of the inputs to stay exactly where they're at. Okay, so this is what they might call a no change situation. Okay, so another way you may see this this table is to say, forget about the current state and next state. You just say that if you have 1, 0 at the inputs, this is going to be we're going to have, how am I? I've got, oh, this is what, if we have 1, 0 at the inputs, the output's going to get set. If you have 0 and 1 for the inputs, we're going to get reset. If we got 0, 0, we got a no change situation. Now, well, what if it doesn't matter what these are? It could be anything here. And if we put 0, 0, well, I'm sorry, if we put 1, 1, that's what I was getting ready to say, but this isn't showing 1, 1 yet. So here, if it was 1, 0, and we put 0, 0, you can go through the logic of this, and it stays the same again. So this 0, 0 at the inputs is a no change state. Here, I'm saying if we get it, I don't care if that's 1 and this is 0 and this is, or this is 0 and this 1. If we put 1, 1 at the inputs, it causes both to go low, and that uh, was. I hate that when that happens. That avoids the definition. That's not the definition. They have to be opposite of each other. So a lot of times they'll call this the illegal state, or something like that. It's not going to hurt anything. I mean, I got an OR gate that's outputting a low and an OR gate that's outputting a low. That's not a big deal. But for a flip-flop that's supposed to have opposite outputs, that's not the correct state. So that is what they would call invalid state, illegal state, or something like that. Violates is that word I was trying to think of that I couldn't get. Illegal or invalid, it doesn't matter, something like that. Okay, so here is the complete table. I wanted to have one table out there that had all this for you, and you could say, okay, this is the one I'm going to use for tests and things like that. Okay, let's look at this one. We're still looking at the NOR SR. What I'm trying to show by this particular slide is here's S. This one's already low, it stays low. This goes high. That forces this one to go high, which forces this one then to go low. Okay, then this goes high, it causes this one to go high, and then that'll force forces this one low, and that forces this one high. So this is just this is a visual of what we were just talking about before. Okay, using NAND gates, this is what you got. Okay, it's active lows. Okay, so here when we had 1, 1 at the input, that was invalid. So here, when we have 0, 0, we got the invalid state. Okay, here we had 0, 0 was a no change state. Here it's 1, 1 is the no change state. And since they're active lows, when you have an active signal on set, it sets it. If you have an active signal on reset, it resets it. So this is a good table to have. Now, some of the tables you might see out there will have, they won't even have not Q on there. They'll have Q sub T, meaning Q before the input's changed, and then they'll have Q sub T plus 1, meaning right after the change of the inputs. This is what they'll be. But it's only showing Q at that point. Okay, now we start putting in a gate, and this is like putting in a, we're starting to get to the point where we're putting in a clock or a edge triggered type device. But this we could call, with a gated input, we could say it's a level triggered device. So here, nothing's going to happen until this gate enables these two NAND gates, and then their output's going to change or stay the same as needed, and apply it to the actual latch. So here's the table for that. If we have 0, 0 on the set and reset, and then the gate gets asserted, then Q is going to go high and Q naught is going to go low. So it's actually it's not showing us the state before. These are actually the no change states. If S is high, we're going to get the thing to go set, and if R is high, we're going to get the thing to go reset. And if we have ones at the inputs, we're going to have that invalid state again. Okay, now this one is just showing another way we could do this. You're going to start seeing these symbols a lot. Okay, and then this is going to show you basically this table. But here we got AND gates and NOR gates. Does that work with this? In a way, it does if you apply some Boolean and De Morgan's. We about got the same thing. So here, if we have to look at the clock or the gate, and if it's asserted, then this thing will work. If it's not asserted, these aren't going to change. So here we've all of a sudden got some, it doesn't matter what the inputs are. If they're both 0, we got a no change state. See, this is Q of t, this is Q before the clock, this is Q after the clock. So this is saying that Q after the clock is the same as Q before the clock, no change. Okay. Here we've got, it looks like a 1 on the reset, so it resets. Here we've got a 1 on the set, so it sets it. So those are active high. And then here we have 1 at the clock and 2 1s at the input, and that's when we get the invalid state again. So it's the same thing as we had here. This is the same, or behaves the same as this one, right? This one and this one behave the same. All this is showing you that now this you got to be careful of. There's going to be things on the test like that set of waveforms, and I'm going to be having these inputs come in, and so you're looking over at this table, and then you say, oh, okay, I see that this changes here. Okay, and now that this is 1 and this is a level triggered device, while it's 1, this thing gets set. Okay, now it shouldn't change at this point until the next time the clock goes high. But while the clock's high, you're going to, I hope, maybe you won't see that in here. If while that clock is high, there is a change on S or R, there's also going to be a change on Q. And I do that to you on those flip-flops on the test. Okay? I do that. I'll put, here's a clock, and I'll have it a real long one, and I'll have either S or R or J or K or D, something like that, change while the clock is asserted. and the input's going to follow, or the output's going to follow the input when that happens. So here we got another clock. Nothing happens during this time because the clock is low. The clock has to be high for something to happen. Here, it's nice, that all the changing is taking place when the clock is not asserted. And here we have S is low. Here we have reset is high. We got a high input from the clock, and we reset the flip-flop. All this happens here, but when this, and so, another thing I want you guys to look at when you're doing this on the test, something like this can make a lot of you go, "Oh crap," right? This looks complicated. There's a lot going on here. There's not as much going on as you think. You only have to look at this point, at this point, at this point, this point, and this point. So I would take out like a colored pen or something and highlight that. Say, this is where I need to focus. This is where I need to focus. Here, and here, and here. And blank out the other ones. Okay? So now, when we're here, when this is high, I see that R is low and S is high. So R is low and S is high, so the output Q is 1, and then by definition, not Q is gone low. I ignore everything else. I look at this next time that it was high. I see that R is high and S is low. I see R is high and S is low, and this tells me that Q goes low. Q went low, so Q naught went high. Here, during this time, I see they're both low. That's here. There's no change, so they stay exactly what they are. And you can draw this line from here all the way to the next one, this one all the way to the next one before you have to check again. Okay? Then you look here, and you say, oh, okay, well, R is low and S is high. That's a set situation, 1 and 0. And so we get 1 and we get 1, or 0 here. And then this last one, they're both high. The problem here is it says that they went 1 and there's a question mark, but what really happened? They both went high. It's an invalid state, but they both went high. So you can predict it. There are some of these that you can't predict because you don't know what it'll do. Okay, now this changes everything here. This changes it to an edge-triggered device. So now everything happens when either the clock goes high or when the clock goes low. So when the clock is asserted, this first stage will be active, and then when this is deasserted, then this thing gets active. So let's go look and see what happens here. Finally, we're getting into some places where we don't care what the inputs are. Okay? I don't see an invalid state here, do you? So they put this gate or the clock in here, this edge trigger, to get rid of that situation where we have an invalid state. So here, if S goes low and Q is low, then Q of T plus 1 right after the clock. And this is an active high clock because there's no bubble on the end of this or no negative input, no bar over this. So if this is here and the clock goes high, as it goes high, it reads S is 0, Q T plus 1 right after that thing went high. It goes stays 0. Here, if S was a 1 and R is low, here it didn't matter what R was. And the input was low, this now goes high. Now take a look here. Here's S, is low. Let's say this was 1. Here it's 1. If the input was 1, it goes low. If this was 1 and it was 0, it stayed 0. So this is what happens here is if you're in this case, it goes low. If you're in 0, 0, it's a no change. So we don't care what R is. Does that make sense? If here we care because the current input or current output is a 1. So if R is a 1, we're going to make it reset. Here, if R is a 1, we're going to make it reset also. But if it was 0 beforehand, we don't notice any change. And 0, 0 is no change. So it's one of those cases where R, we just don't care what it is. Here's a case where if we had 1, 0, we set this thing. If we have a 1, 0 here, we still set it. But if it was 1 beforehand, it doesn't change states. It's still set. So we really don't care what this is. This is at 0, 0, and this could be that 0, 0. I hope that makes sense. If it doesn't, this would be a great time to say, wow, you could tell me how to do that again or something, or, you know, let's work a quiz or something like that. You have homework on this, don't you? You should have some homework coming up. I love the D, don't you?
No, actually, I don't.
Why not? The D flip-flop is the best. It's the easiest. It's a little more complicated on the inside, but they put this in there to make sure that S and R inputs are never the same. And it's to me, it's so easy because it doesn't matter what the input was. If you put a D on the, or I'm sorry, what Q was, what the output was beforehand, if you put a 0 on the input and then clock it, the output goes to 0. If you put a 1 on the input and clock it, the output goes high. This could be an active high, it could be an active low. The thing is, when you clock it, that's when the change takes place. These are edge-triggered devices. Okay, now here, I've done this on the test before, this exact circuit. Okay? Okay, now's a good time to ask questions, yeah.
So have you decided what we're gonna, if you're gonna put the test online, or if you're gonna?
I want to have the test online. I don't know if I'm going to have time to put the test online. I want it online for my DE students so that they just don't have to worry about it. Otherwise, they're going to have to download a piece of paper. They're going to have to work it out. They're going to have to make it very clear so I can read it. And then they're going to have to scan it and email or send it back. Or they're going to have to type it all in Word. And I don't want them to have to do that. And I do all my tests as time tests. So I'm going to try my best to make this a online test, and I think I can do that. But damn, my paper tests are harder, and I just love that. I just love them to be harder. No?
I like it.
You know, if you guys have these blank credit cards or you've got dollar bills that have 1 and then lots of zeros, I was telling you about that the other day, wasn't I? If they landed in my pocket, the test would get easier. The more of those zeros that appeared after the 1s, the easier and easier this test would become. In fact, when you reach this tipping point, it's just everybody that, you know, contributed to the cause gets hundreds. I want to be very clear that I am kidding. I want to be very clear that I am kidding on this because my I had a group a long time ago at Central Piedmont that put like $3.53 up on the desk. And when I walked in, it was like, oh, hell, that's not my cash. I'm not touching it. You guys get it away from me. I'm not accepting any bribes. And I wouldn't do another thing until they got rid of that money. And it was only like $3.
Steve, can we buy you a handle?
Do you see how many people can move quicker than I can? So Sherlock will die. He'll hear that hit the floor, and he'll dive out of his office and get it before I can.
If we accidentally drop it, just randomly slid under the door,
No,
and then slid all the way to
my tests are not that hard, and you can always use everything that's on the web to do it. And I am one of those. I'm one of those that you have probably seen these questions or something very similar to it either on the slides or in the homework already. So you've done something very similar before you actually do it on a test. Now, let's look how this thing's happening. We got 3 different flip-flops here. I'm not going to spell it out what kind they are. I'm just going to give you the symbol. Now this one says clock. This one has a little triangle. And this one has a triangle with a bubble. And they're all connected to the clock. This one, the one that's just the clock input that doesn't have anything else there, is a level triggered. So anytime, and because there's no bubble here, this is a high level triggered. So anytime that the clock is high and D is changing states, so is the output. But when that clock goes low, D or the Q stays where it is. Okay? Until the next time it goes high. This is an edge triggered device, the one with just the little triangle there is an edge triggered device, and it's a positive edge triggered because there's no bubble there. So when you get the test and you look at this, you say, I only care at this point and this point. I don't care at any other point. All I need to do is look at what is D at this point and what is D at this point. The rest of it is just noise to confuse you. Here, we got the triangle and the bubble. That's a negative edge. So we're concerned, or we need to focus when the clock is going low at that point. And at this point over here where the clock is going low. Again, the rest of it is noise to confuse you. So here I've got QA, QB, QC, all 3 of them in one diagram. Here's D. D's coming along. It goes high before the clock does. And let's just look at the first one. Let's look at the first D flip-flop up here, the level triggered, positive level triggered. And D's already gone high, but when the clock goes high, then all of a sudden this flip-flop becomes active. And since D was already high and Q was low beforehand, Q jumps up to a high level. And this whole time that this clock is high, the output Q is following what the input D is. Okay? Right here, where the clock goes low, the D flip-flop stops. It's disabled for a while. So the Q stays exactly where it was before. What are you guys looking at on those computers? If you're smiling, you're not looking at digital. Digital doesn't make people smile.
Starlink is just crashed
just
on
crashed
me.
on
And that makes you smile?
That was the angry smile.
Oh, an angry smile.
I was
Yeah,
driving
exactly.
and I forgot
Okay,
to say
Xilinx just went away on you. Isn't that nice? Okay. Here, the whole time that the clock is low, Q's changing, or I'm sorry, D is changing, doesn't matter. Q stays exactly where it was before. So if I were looking at this test during this time, I would have Q follow D, and then right when it goes low, I would draw a line from there right till the next time that the clock went high. And then when it went high, I would start following Q again. And here, Q is high, the clock is disabled, but Q remains high even though D goes low here. For the second one, we only care about this point and this point, the 2 points where the clock goes high. For this first one, when the clock goes high, D is high. So D or Q goes high for that one. At the second time that the clock goes high, D is low, so Q goes low. That's all we have to care about. The third one, it's just traveling around the room, isn't it? The sneeze. So here we don't care about this. QC was low here. It stays low all the way up into here. Now we're getting a change on the clock and active. It goes active low. So now we got to look at what's D. D is low, so it stays there until we get to the next time that the clock goes low. Here it goes low. D was high, so Q finally goes high. This particular page is worth understanding for the exam.
What are you trying to say?
So here I'm trying to finally tell you we get level triggered, we got a positive edge triggered, and we got a negative edge triggered. Here is the JK. It is a nice little flip-flop. It goes all the way back here. It's connected from this output actually all the way back to the first input. So there's a lot of feedback here. This is not, I've seen JK tables look a lot different, but here it's saying that if the output is currently 0 and J is 0, it doesn't matter what K is, the output's going to stay low. So this is a basically with 0, 0 at the inputs, we're at a don't care or a don't change state. Here, if we put a 1 on J, it sets it. So here it's a 1, it sets it, it doesn't matter what K is. Now, when we've got a 1 currently at the output, it doesn't matter what appears on J. If K is a 1, it resets it. If K is a 0, it sets it. Okay, I wish I had that in a way that's a little bit simpler, because the best way to say this, and I don't have it this way on these slides, is if J and K are both 0, we're in a no change state. So you're going to have to write this down or something because I don't have it in the slides. But this is an easier way to look at it. Forget what the output is to start with. If J and K are both 0s and we get that edge triggered, the output doesn't change. It stays the same. If J is 1 and K is 0, we go to the set state. That sets this thing. Okay, if J is a 1, doesn't matter what k is, it's going to set this thing. Well, let's just say if j is a 1 and k is a 0. If k is a 1 and j is a 0, we're going to reset this thing. If they're both 1, it toggles. So let's see how that works with this one. Here I said if they're both 0, we get a no change. So we have a 0 before the clock, a 0 after the clock. Here we got a 1, and I said if j was a 1 and k was a 0, we would get the set. Well, here q was 0, it went to 1. Down here, if j was 1 and k was 0, it would also go to 1. If this was 1 and that was 1, we toggled. It went from 0 to 1. Here, if j is 0 and k is 1, it resets it. If they're both 1, it toggles. If j is a 1 and k is a 0, it goes to a set state. If j is a 0 and k is a 0, it goes to a don't change state. So this could also say 0, 0, don't change. If j is a 1 and k is a 0, we set it. If k is a 1 and j is a 0, we reset it. And if they're both 1, it toggles. This, to me, is the easiest one to get messed up for or messed up on the test. If I have one of these on the test, there's, and this table is even difficult to interpret. But what it's trying to tell you here is if t is 0 and we get a clock, the output stays the same. Q after the clock, that's t plus 1, is the same as Q before the clock. So there's a no change if t is 0 and we get a clock. Here it says if t is a 1, then the output is Q at t plus 1, but at t it was Q bar. What it's trying to tell you here is it toggles. So this one, when the input is 0, it stays the same. When it's a 1, it toggles. And that one, people want to always put a 1 when there's a 1 on the input. But this one says every time you see a clock signal, it toggles. Okay? So here's one. It shows positive edge triggered because this is a triangle with no bubble on it. T is 1, so Q toggles. Goes from 0 to 1. The next time I have to look is right here where the clock goes high. And at that time, T is 0, so it doesn't change. So I can draw a line all the way over to the next time that we get a positive edge clock. At that time, T is 1, so it toggles. I don't know what happened, but they're all not taking blame for it. It's all your fault, right? Here we have another. So again, since T was 1, it toggles so we can draw it low and then draw that line all the way over to the next time we have a positive edge on the clock. And then here, since T is high again, it toggles again, and we draw that line all the way over to the next time that there's a change on the clock. Okay, there's some of the terminology I've been using. And now we're going to go into these counters. Now, I'm going to save counters for after the break. Thursday next week, you're going to want to come in, and the DE students are going to want to maybe email me some questions over the practice exam that's out there. If you haven't got it yet, go over it, look at it, figure some of this stuff out. Okay, this is all the stuff that we've talked about. Here's decoders, here's adders, here's SRs, here's a D. Is this a positive edge, negative edge, or positive or negative level? That's a positive level. Here's a positive edge triggered D. Here's a negative edge triggered D. Here's a negative edge triggered T. Ooh, a JK that's positive edge triggered. And I put these down here hopefully to help a little bit. Okay, so practice with that. If you have any questions, I'm not going to answer them until that Thursday. So if anybody emails me questions, I'll just wait. All right, and then we look for the test. What, the next Thursday? So we come back on Thursday. Let's go ahead and look for the test on Tuesday. Okay? We got to get this test. Huh? Look for the test on the 14th. Look for the test on the 14th. All right. And for my DE students, that's my little granddaughter, and she's the cutest baby alive. Say anything different, and you'll fail the class.